Theorem, core of a convex game, will show that the core of a convex game is non-empty. So that's the statement of this theorem. And in order to show that it's non-empty, all we have to do is define some pair of vector x that is efficient, individually rational, and group rational. And thus, it belongs to the core. And therefore, the core of the convex game is non-empty. So all we have to do is define such a pair of vector x. So this is how I define my pair of vector x. x1 is v1, x2 is v12 minus v1, and in general x sub I, the payoff of agent I, is v of 1 to all the way to I minus 1 comma I minus v12 all the way to I minus 1. And until xn, and I write down the general expression for xi because I'll be needing it over and over again. So first I have to prove that it's efficient. Now I've written down this is the general expression for xi, and x1 is v1, x2 is v12 minus v1, x3 is v of 1, 2, 3 minus v12, and so on. And now, in order to show that x is efficient, summation of xi must be equal to the value of the grand coalition n. And now if you look at the right hand side, v1 and we have a negative v1 here, so they cancel out. Likewise, v12 and negative v12 cancel out. This and this cancel out, this and this cancel out, and finally on the right hand side we are left with v sub n, whence summation xi equals v of n, which shows that x is efficient. Next, we have to show that x is individually rational. Again, using the expression for xi, we have xi equals v of 1 to all the way to I minus 1, then I minus v12 all the way to I minus 1. And this I rewrite in this form, v of 1 to I minus 1 union I minus v1 through I minus 1. And I let this, what's colored in blue here, be the coalition C. C is 1 through I minus 1. Whence I have xi equals v of C union I minus v of C, which is equal to, by definition, this is the marginal contribution of agent I to C, this expression here, which is delta VCI. So I have xi equals delta VCI. That's one expression that I'll need. Now, value of the coalition consisting of I alone is equal to value of null union I minus v of value of null. Why is this there? It's equal to 0. As per our original assumption, the value of the null coalition is 0. And so this is v of I, whence v of I equals delta v of null I. So it's the marginal contribution of agent I to the null coalition. This is the other expression that I'll need. These are the two expressions, this and this. So from convexity of this game, we have the marginal contribution of I to C will be greater than or equal to the marginal contribution of I to any of its subcoalitions D. In particular, letting D equal the null coalition, what we must have is delta VCI must be greater than or equal to delta V null I. But if you look at this left hand side, it's equal to x sub I here. And if you look at the right hand side, it's equal to, from this expression, v of I. Whence we showed that x of I is greater than equal to v of I, which proves that x is individually rational. Part 3 of the proof is a little more involved. So this is my grand coalition. I have taken all the agents indexed 1, 2, 3, 4, all the way to n in sorted fashion. And so this is my grand coalition. And then I form a subset out of this called C. And in that subset, I take these agents which are colored green or blue. I1, I2, I until ik minus 1, then ik plus 1, and so on. And these indexes are again in sorted order. I1 is less than I2 is less than I3, and so on. And this is what I have to show to prove group rationality. Summation I belongs to C of xi is greater than equal to v of c, and this is what the expression for xi is. Now, this is the coalition C. I have taken all the relevant agents indexed I1, I2, ik minus 1, ik, and so forth, and formed this coalition C. And then I define these coalitions D and E. E contains all the agents from 1 through ik minus 1 of the grand coalition, and noting that this is this until this point, this is my coalition C. D is a subset of C. It's the subset of agents I1 through ik minus 1. I have some sort of a cutoff I of k here. So this is my D. It's a subset of C, and it's equal to I1, I2 until ik minus 1. All the agents in C until the k minus 1th agent. The rest are not included in D. And in E, I have included not just I1, I2 until ik minus 1, but 1, 2, and I1, I2 until ik minus 1. These are all the agents in the grand coalition until ik minus 1. So D is a subset of E, which is all the agents until ik minus 1, not only the agents that belongs to C until ik minus 1. So D is a subset of E. Whence, since this is a convex coalition, the marginal contribution of agent I to E will be always greater than equal to the marginal contribution of agent I to D, because the D is a subset of E. Replacing I with I sub k, I have this expression right here. Now, on the left-hand side of this inequality, I have V of E union ik. E union ik contains all of these agents, including the blue one, ik here, minus V of 1 through k minus 1, that's value of E here, greater than equal to value of D union ik. This is D. D union ik is all the way until this point here, these and this blue one here, minus V of D. D is everything that's green here. This is D. V of I1 through ik minus 1. So I get this inequality here. Now, by definition, uh, the way we formulated x sub I, what's on the left hand side is x sub ik. It's the marginal contribution of ik to this uh, coalition 1 through ik minus 1, 1 through ik minus 1. The marginal contribution of ik to this coalition here, E, and that's xik, and that's greater than v of I1 through ik minus v of I1 through ik minus 1. So I arrive at this inequality here. X sub ik is greater than equal to value of I1 through ik minus I1 through value of I1 through ik minus 1, which is d here. This is d union ik, and this is d. And I will now apply this expression, this inequality, to I1, then to I2, and so on. Letting ik equals I1, I have this expression right here. Now here, notice that D will be equal to the null set, and to that null set, I'm adding this agent I1. Next, xi2 is equal to v1, v2 minus v I1. So this is my D, only this much. To that, I'm adding I2. So this is my xi2. And I keep repeating. xi3, I have this expression. And at the very end, for the last agent, I sub c, I have this expression here. xi sub c is greater than equal to v of I1, I2 all the way until IC minus VI1, I2 until IC minus 1. Now, I1, I2 until IC is basically the entire coalition C. So this is what I have. Now, let's add up everything on the left-hand side. xi1, I2, from this point, xi1 until xic. So this is equal to summation I belongs to C of xi. I'm adding up all the x's, the payoffs of the agents which are in my coalition C. And on this side, I can, when I add up, I have this greater than equal to. And on this side, I see that things cancel out. VI1, negative VI1, VI1, I2, negative VI1, I2. So everything cancels out, and all I'm left with is V of I1, I2 until I sub C. So this is what happens on the right-hand side. But we saw that I1, I2 until I sub C, these are nothing but these agents which are part of the coalition C. So this is on the right hand side, I have the value of the coalition itself. And on the left hand side, I have summation I belongs to the coalition of xi. And this inequality here I just showed is basically group rationality. In other words, I showed that if we form x's in this manner shown here in gray, then group rationality is valid. Whence I have completed my proof. I proved part 1 that it was efficient, part 2 I proved that x was individually rational, and part 3 I proved now that x is also group rational. So I conclude that the core of a convex game is non-empty. This is the statement of my theorem, which I just proved. A little word of caution. A convex game has a non-empty core, but it doesn't imply that any game with a non-empty core is necessarily convex.